Hopefully the recordings will be there. So okay. So yeah. So what? Okay. So this kind of completes the part on multi-agent search. So this is going to form your next lab assignment. Actually, I wanted to release it in this week so that as I'm teaching this, you can parallelly try this out. But I guess people are still working on the first lab assignment, so I didn't want to kind of scare them and give like too. I mean, I didn't want to make it stressful for them. So I'll just tell you the assignment right away. So I'll just informally tell you. So I will release it by end of this week, formally, so that it's there. But for those of you who have completed the lab assignments one, this P2 of the Berkeley projects is the next set of assignments. So you will have to implement. One is a very kind of ad hoc reflex agent, then all these concepts, min-max, alpha, beta, pruning, expecting max, and you'll also design evaluation functions. So you can start going through this if you're already done with your first lab assignment. Okay. So I will give, like, from next week, I'll probably give you about 2 weeks or so for this assignment. All right. So, okay. So moving on, let's start the next level of complications to the model, or sophistication, I should say, not complications. So that's going to be a topic called MDPs. Couldn't see the cursor. I don't know if I'm going blind. Okay. Yeah. So what we will see today is a topic called Markov decision processes. So, yeah, this is actually another way to model problems that you see in AI. So, these problems arise when you have like a recurring process. There are like over multiple time steps, there is something going on. And at each stage, you want to decide on a good strategy. Okay. One difference from all that you've seen so far is like, okay, you really didn't see a lot of randomness in the search space, right? In the kind of models we had, there was a state, you took an action, you reached the next state, then maybe you or the next agent took another action, and where you're going to head is always clear. If you take an action at a state, it's very clear to you which state you're going to land up. Okay, so now suppose, I mean, many times you don't know that. Okay, so in a lot of problems, what happens is there is some randomness in the environment itself. There is some external factor due to which, if you take an action, you don't know exactly where you're going to land up. Okay, so there is some randomness, and in the presence of this kind of randomness, how do you decide what is a good strategy to take, and how do you plan your actions? Okay, so that is the broad idea of MDPs. So you can think of these as a non-deterministic search problem. So I will take a concrete example in some time, but let me just tell you, like, since you've already seen search problems, I just want to tell you where the difference comes. So non-deterministic search problems. Okay, so that's what this kind of models. And so what all did you have in the multi-agent search, for instance? What were the components? Can you just tell me? You had states, actions, and all, right? So can you just formally tell me what were the components you had?
The state, players.
States. Okay, so you had players. So we don't explicitly account for players in this model. And what else did
Utilities.
you have?
Utilities.
Utilities. So you
Transition
had,
function.
yeah, so utilities, then you had states, you had actions, right? And you had utilities, you had a transition function which told you, um, if you take a state S, and if you take an action, where are you going to be? So this was actually also a state. So that was in the original search problems that you saw so far. Okay, and then you had a utility, and okay, you had this notion of terminal states, and there was this concept of utilities for the terminal states. Now there's going to be a slight difference. So what you're going to have is the transition function. So I will just remove this for now. We'll come back to it. So for the transition function, what is going to happen is you exactly don't have a state. You are in a state at the moment. Now you take an action. Here, you don't know for sure what the next state is. There are a couple of possibilities. So you can go to any of these states. So you can be in state S1 or you can be in S2 and so on. This is not known to you, but there's some probability with which this happens. Okay, so instead of saying the exact state to which you will land, what you're going to have here is a transition function which takes the current state, an action, and the landing state, so S dash. So this is just the probability that you will reach the state S dash, given you started off with S and you took the action A. Okay, so yeah, maybe I'll just do an example of this. I'll just come back to this one. And another point here that you have, which was not there in the search problems, was what is called a reward function. Okay, so it is like the utilities, but there's a difference here. So the reward is something that is given for each transition. So you are in S. If you take an action and go to S1, what is the reward you get? It's associated primarily with the action. So R, SA, and S dash. Okay, so this is the reward. If you start at S, take action A and reach S dash. So if this event happens, then you are going to get this reward. The reward is this, and there's also another concept of utilities which we will come to apart from the rewards. Okay, so you can see now that every move in this kind of a game has some kind of benefit. Okay, and that's what we are capturing. And you also have start state. Okay, and in the other case, you had terminals, right? So terminals is not always necessary to be here, but this is an optional state which may or may not be there. So here you can see the problem is not to get to a goal state. It's usually to maximize your reward functions, or choose some set of actions so your reward is maximized. So okay, so let me take an example without I'm just speaking so much about these notations and things like that. So an example will perhaps make it more clear. So what I'm going to do is I'm just going to use an example which is also used in the Berkeley lectures. So I'm doing this so that you have something to refer to. There are a lot of examples of MDPs, like in queuing and scheduling, like there's so many examples, but I'm just using the one from the Berkeley lectures itself. So this is an example where you're trying to design a robotic car. Okay, and the robotic car is there are a lot of parameters here, a lot of design issues, but you are just looking at keeping the car in a non-overheat state. Okay, so the car has 3 states. So there is a cool state. So maybe let me just write it here. So the states here there are three possibilities. So either it's cool, okay, or it's in a slightly warm state, or it's in an overheated state. Okay, so we don't want this overheated state. We always prefer either a cool or warm state is fine. If it's overheated, the car just is going to stop working. Okay, so these are the 3 states, and the actions you can take. You can decide as an agent. You can decide whether you want to go fast or slow. Okay. Now, depending on what action you take, sometimes you will, different things can happen, right? For example, it's not that, if you always go, every time you go fast, you may not go into an overheated state, right? After some time, but sometimes it happens. Okay. So that's where this randomness comes in, the states and the actions. Was there a question? Somebody unmuted? Okay. Okay. Fine. Yeah. So I'm audible, right? Just want to ensure
Yes.
that I'm still here.
Yes, ma'am.
Okay. Okay, fine. So, these are the states, and having said the actions, let's see what the dynamics of the system is like. Okay. So, when you start off, maybe you're in a cool state because the car has been parked for some time, so it's cool. Now, if you decide to, keep going slow, what happens? You'll stay in the cool state, right? Um, and this is going to be with probability 1 itself, right? But however, if you go fast, what happens, right? Um, right? Sometimes you will, maybe there is going to be a warm state and maybe an overheat state. Okay, I'll just write it as O. So, oh, okay, fine, overheat. Okay, so yeah, so when you take a fast action, if you decide to go fast, so sometimes you will go to the warm state. Okay, so maybe with probability half, you will go to the warm state. But sometimes when you go fast, also you will still be in the cool state, right? So, so yeah, so you see that for each action, there are two possibilities here. So either you could be in cool or you could go to the warm state. Now, yeah, so we have covered all possible actions for the cool state. Now, in the warm state, what happens? If you go slow, what would happen? A lot of people who drive cars here, right? So you should tell me what happens.
It should remain warm or maybe return to cool.
Yeah, so if you go slow, so this is if you go slow, maybe a half probability of staying warm. And maybe, yeah, you can have a half probability of going back to cool. Okay? And what happens if you go fast in the warm state? Can you go to cool from the warm state if you go fast?
No, ma'am.
It doesn't happen, right? So the possibilities are what?
Stay in the warm
Over
state from the over.
Overheated.
Or overheat, right? So maybe a fast, if you go, maybe there is, I'll just change the numbers for to make it a little more, diverse. So maybe with 0.4 probability, you stay in warm, and maybe with a probability 0.6, you go to overheat state. Okay. Now, for this example, an overheat is, you can think of this as your terminal state, but this is not a desirable terminal state. Huh? So this is like once you reach the overheat state, there is no action. There's nothing to be done. Okay, because the car has been damaged. Okay. Um, right. So this is, showing you, giving you a sense of the transition function. So where you have these probabilities associated with each of these actions. And there's another point we said about rewards, right? The reward function. So remember, the reward is something that you associated with each of the actions. So, for example, if you are in a cool state and you go slow, right? What's the reward? I mean, you're ultimately you want the car to move. You want the car to head quickly to some destination, to head quickly somewhere, and but you want it to be in good condition, but in good condition, in good condition. Okay, so this is the objective of this model. So the reward. So if you are in a cool state and you go slow, maybe and you come back to cool, maybe the reward is say 1 unit. Okay. Now, if you go, so now the remaining actions are fast, right? So if you go fast and you go to a warm state, maybe, again, the reward is, say, something like, I don't know, is it better or not good? What is your sense of it?
It should be better.
Yes, ma'am.
Better? Yeah, it's better. So warm is still okay, right? So maybe we'll make it 3. Okay. And what about this? If you go fast and come back to the cool state,
Better than going to warm state.
better than going to warm state. And so maybe we'll keep this reward as 2. Better than warm state, right? So maybe
Yes.
make it 3, 4, I guess. Okay, we'll make it 5. Much better, right? Okay. And then what happens? So what about this action? You're in a warm state. If you go slow, you come back to cool. So what do you think? Is that good? Is it bad?
It's bad in the way we are slowing down, and it's good in the way we are cooling down.
Yeah. So maybe let's keep the reward as 3 itself. Okay. And now maybe in the warm state, if you go slow, you remain here. So maybe that is, I don't know, it's not that good as this point, right? It's better to come to cool. So maybe this is a reward of 2. And if you go fast and you stay in warm, that is fine. So that is a reward of maybe 4. Okay. And this action, if you go fast, you end up in overheat. This is clearly bad. So this has a reward of maybe it's a -10. Okay. So, right. So here you see that, with each action, there is potential for different kind of rewards. So in the cool state, if you took the fast action, there is some reward. If you took the fast state and you reached a warm state, there is some reward. If you took a fast state and stayed at cool, there is some reward, right? So there are these different rewards which also depend on the start state. On where you started from, where you reached, and also the specific action. Okay, so this is just an example model for a Markov decision process. Okay, so now there is no notion of a goal state here. It's not that so of course you definitely don't want to reach the overheat. So this is like a terminal, and here, it's a bad terminal state. You don't want to get there. So what is the objective here, right? At each point, you want to see what is the action that you should take, so that over a period of time, your rewards are as large as possible. Okay, so I also just want to come back to this transition function, right? So we told that we have this TSAS dash, which is the probability of reaching S dash given that you are in a state S and you take an action A. Okay, so now you all have done a probability class, right? So what kind of a probability is this? There's some name for this kind of probabilities, right?
Condition.
Yes, exactly. So this is a conditional probability. Okay, and so what is the random variable here? Is it
S dash.
S dash, right? So what about A? Is A random?
S and A are given to us, right? So
Yeah, that's true. S is okay. So let's do this. For sure, states are random here, right? That is something we all understand. So the state evolution is a random quantity. Now here what has happened is a particular realization. So S is a particular realization at some point that has been given to you. Okay, so let's I hope that's clear. And what about actions? Are actions random? What do you think?
I don't think, ma'am, because actions will decide according to a situation.
Yeah, exactly. So yeah, actions are not random. So actions are the decisions to be taken, right? So these are not random. So I just wanted to, explicitly point this out because sometimes people get confused when you write it as a probability, right? Usually, when you say conditional probability, you say it's conditioned on a random variable taking some value. Okay, but here when we say this, it doesn't mean that A is a random quantity. It's just that you took this action. It's some information that's given to you. Okay, now. Okay, so you all know that probability distributions have the summation equal to one, right? Very loosely put, if you have a probability distribution represented as a vector, all the entries have to sum to one. So here, something sums to one, right? So probability of S dash given SA. So what is the summation over? If I sum over what, should I get one?
All S dash which are possible.
Yes, all S dash. So all states S dash, which you can reach with action A. All states S dash reachable with action A, right? With action A. Okay. So if you sum this, then you're going to get a value 1. Now, what about this summation? So probability S dash given SA. So if I sum over all actions, is there something I can say? Is this going to be 1?
That would give us how likely are we to reach S dash if we are in state S.
How likely are we to reach
S
S dash
dash given that we are in state S.
given that we are in state S? Okay. Yeah. So does it have to sum to 1?
No.
No, right? Yeah, exactly. So this does not sum to 1 because what your distribution is over, all possible states that you can reach. It's not over all possible actions. So for a fixed action, what are the possible states? So that's why, you have this summation over S dash is 1, but not over A. Okay. Now, what about this probability? Probability S dash given SA. Is this equal to 1? Okay, I have to ask somebody. Maybe Himanshu? Himanshu, you're there?
Yes, ma'am.
Yeah. So, what do you think? Does this have to sum to 1 or no? So let me tell you. So we are in S. We're taking an action and we're getting all possible. So these are all the possible S dashes, right? So the question is, if you take the summation over all these S, now you're fixing an S dash and you've fixed this action. So S dash is here and you've fixed the action. Okay. And now maybe there is an S1, S2, and so on, which brings you to S dash. Okay. So does this probability have to sum to 1?
No.
No, right? Yeah, because the dynamics is different. So you can just think of this example here, right? So let's say okay, I think here there are far too few states. So, yeah. Yeah. So the essential point is, your transition function, the way you're defining it is like, for a state, for an action, what are the possible next states that you're going into, right? So this is the probability, right? And so you're always assuming that this start state is a given quantity, right? So you needn't sum to one at all. Like, for example, okay, let's take this overheat, right? So there is one action which comes to overheat. So if you look at probability of overheat given S, some states, the start state, and a fast action. Okay. So this is what you're summing off is where did you start from? Okay, so here there was only one possibility. So if you started from cool, you could never directly get to overheat. If you started from warm, you could get to overheat if you went fast. So this probability here is just 0.6. Okay, so it's not always guaranteed. You may not even have some actions possible from different states. I mean, you may not even be able to reach the overheat state from a couple of states. Okay, so that's why this doesn't need to sum to 1. Okay, so the only quantity that is for sure guaranteed to sum to 1 is over S dash, if you take the summation over S dash. Okay, so is this distinction clear to you all? If you are like very quiet,
Yes, ma'am. It's clear.
it's clear. So I also want to hear from all of you. Maybe can you just type in the chat box here? Okay.
So if the file is there, you don't gain access to it. What is the purpose of
Okay.
if the file exists, what is
Okay. So a lot of you have again dropped off. I think it's the connectivity issues, maybe. Okay. So so this is the basic model, and now what are we trying to do here? We have this kind of a model. What do we want, right? So this is where the notion of time steps or time horizon comes in. So the notion of time steps. Okay, so this is kind of like a process which evolves over some time. So at time equal to 0, you start off in some state. Then maybe you start off in the cool state. At time equal to 1, I mean, you're in the cool state, you take some action. Maybe you go slow. And at time equal to 1, again, you are in cool state. Okay, then now you decide to go, maybe you decide to go fast. And at time equal to 2, maybe you reach slightly a warm state. Okay, and maybe you go slow, and then at time equal to 3 you reach a cool state, and so on. Okay, so there is this kind of a clocking that happens, so because of all these times, right? So you've learned about clocks, right, in digital logic. So you all took the digital logic course last time, so you learned, yeah, so you had a clock, right, for the system, right? So the idea is essentially the same. You have a clock which is running, which is keeping track of the time, and it's to synchronize everything else. So all actions, all states that you land to, there is this reference to this time step. Okay, and so that gives you a a common point to tell where you are at at any point. Okay, so what you essentially want is, okay, this can be a process which goes on and on. It can go all the way till infinity. Okay, so very loosely put, it can go till infinity. And or sometimes, I mean, okay, so in this kind of an example, if you hit an overheat before, then you will the process will terminate. You don't go till infinity, but that's not a desirable thing. So in general, it can go on and on. And what you have is also a notion of utility, right? For at each time, depending on the action you take and where you land, you're going to get some reward. Okay, so here you're going to get some reward. So I don't, what was this number we did? Like if you took cool, I mean, if you were in cool, you went slow and reached cool, what was the reward we had? Can somebody tell me?
So now,
Okay.
One.
one is not
One,
One,
right?
yes.
One. Okay. So this was the reward. And in this state, so now you were in cool state, you went fast and reached warm. What was the reward?
3.
3. Okay. And so this process goes on. At each action you take, you're going to get some rewards. And finally, you want, the overall rewards to be as good as possible. So here is where we get to this notion of utilities. Okay. So is it that you want, so at time t0 you're getting a reward r0, plus at time t1 you're getting a reward r1, and so on. Okay, so this r2, r3, and you could just sum this up. But there is an issue with this. Do you see what the issue could be?
We can get an infinite value.
Exactly, right? So this can go to infinity, and it will most likely go to infinity in most cases, right? So we need to do something else. So the overall utility is it's something that should consider the rewards at every state and at every action based on what you get. But you cannot just do a summation. You need to do something a little better. Okay, so I just want to pause for a minute and ask if there are any questions, because the class has been like extremely silent. Is there something you want to ask or clarify? Maybe let me ask Jaishika. Is nothing's clear? Jaishika, you're there? Yes, it's clear. Okay. What about Rajat? Rajat, it's clear. Maybe Rishabh?
Yes, ma'am.
It's clear. Okay. Okay, fine. So, yeah. So, okay. Yeah, so these utilities, there's something better you have to do about this. So typically what happens is, if you let's just consider, what is preferable, what we want the system to model. Suppose you had like rewards in this way. Okay, so maybe for a long time you had 0 rewards, and then you had a reward of 1. Okay, so I'm just considering 5 time steps. So suppose this was my reward sequence, and versus suppose I got something like this. I got a reward at the first time step itself, and later on I got nothing. So which do you think should be preferable?
The second one.
Yeah, because you get something immediately, right? And you can guarantee yourself, an immediate reward. So you want this to be higher. Okay, this is more, let me just say it's more preferable. So what we are trying to do here is now we are just trying to come up with a suitable utility function which takes into account all these rewards at various time steps, and construct what is more desirable for us. Okay? Of course, if you take the sum, that is desirable in the sense of it will give you an overall good rewards, but you won't be able to distinguish between these two if you take the sum, and of course it can go to infinity. So if you have something like 0 0 0 0, and then you get a lot of rewards, versus 1 maybe 1 1 1. Okay, so this is all ones. At every state you got a 1. So this is something like between these two. I mean, if you just take the sums, you will not be able to, it will not converge, right? Both these will go to infinity. Even though initially you don't have, much here. And you have 4 zeros here. So actually this, the first one has to be penalized But if you just take a sum, it doesn't happen. So this is something you have to consider while designing your reward. Now, one way to do this is to ensure that you have a dampening factor. Okay, so you multiply each of these quantities with. So you initially start off with a reward R0, take it fully, but in the next time step, if you're getting a reward later, you try to decrease its value little bit. So maybe you take it as some gamma times R1. Okay, and maybe for the second time step, maybe you reduce it even further, like some gamma square R2, like that, where gamma is a value strictly less than 1. Okay, so if you do this, what is going to happen is, for maybe let's just take this one. Okay, so 1 1 1 1, the reward sequence 1 1 1 1. Let's take gamma is maybe 0.75. So what will happen is the utility sequence here, the utility evaluates to 1 plus 0.75 plus 0.75 square, like that. Okay, and yeah, so what is going to be the value of this? Can somebody tell me? Is this going to be infinity or it's going to
Four.
converge?
Sum of infinite geometric progression.
Yeah. So if you're, so the maximum, suppose the maximum value is R max. So what you're just going to have is R max by 1 minus gamma, right? So R max is, each of this now here is 1. So R max is 1 here. But in general, if you had a sequence like this, R0, R1, R2, etc., so the utility would look something like this: R0 plus gamma times R1 plus gamma square times R2 plus so on. And what this is going to, if you had instead that instead of R0, you had an R max. So this is the maximum value of the reward, maximum possible value of the reward. So for this example, I think we had 5 was the best possible reward at each step. Okay, so if you take R max at every time step, so this is going to be less than R max plus gamma times R max plus gamma square times R max, right? Because each of the rewards are going to be less than R max. And so this is a geometric series, the last one, and that will evaluate to R max by 1 minus gamma, and this is a finite quantity. Okay, so that is an advantage of going with this kind of dampening effect. Okay, so yeah, I hope this notion is clear to you all. I think we are also running short of time. So, okay, so what I'll do is maybe I'll just stop here for today. Okay, just setting up the framework of Markov decision processes. So I will continue from here on Tuesday. Okay, so if there are no questions, thanks everyone. And yeah, have a good weekend later. Okay, so thanks. Yeah.
Maybe it's catching that, yeah, run dependency, let us see if it throws any exception. But it won't throw an exception, it will throw an error if it is not there.